So Douglas, well, let me read it a little bit. Douglas is a culture and sustainability specialist. He worked in the museum field for 30 years. He spent 15 years looking at the relationship between sustainability and culture. He was invited to join the Leadership for Environmental and Design back in 1997, around the time of the Earth Summit, just after the Earth Summit. He also has been focused on understanding the links between culture and sustainability. If you're interested in whiskey history, Douglas Worts is connected to the distillery district, and my guess is your family probably put up the very first wind turbine in the city.
That's true.
Which was,
windmill.
Sorry?
The old windmill.
The old windmill, which was used to mill the grain, which then led to the opening of the distillery. But that's not what Douglas is here to talk about tonight, so I'll turn it over, Douglas.
Okay, thank you.
Thank you.
Well, it's a pleasure to be here and to be here connected with another event that has links to Project Neutral, because I've done some other things with Project Neutral as well, and even we'll have a little reference to something that popped up kind of in relationship to it over the Riverdale side. So this is, I was asked to come in to talk about a couple of things, and one of them was to tell a bit of the story of Green Laurier, and I will do that. That's a little project that we have going between 2007 and 2011, I guess, before it ran its complete course, and it was an adventure into the world of geothermal heating and cooling, and so lots of twists and turns in that story. The other thing that I was asked to do was to just provide a bit of an introduction, like what is geothermal, and so those are the two main things that I wanted to do tonight. So the overview, what is geothermal and why should we care? And so we'll address that question first, and then tell you a bit about the Green Laurier story. And then there's this question about geothermal as a standalone energy system for an individual building or a district one. And so that is another thing I was asked specifically to address. And what are the challenges? What are the opportunities? And it remains an exciting prospect for the city. There are some interesting things going on. And to have some discussion, find out what you're interested in, and see if I can answer questions. And I'd like to hear more of what's up with you. So just a little bit about heating and cooling, and there's been a long history in humanity of using burning things essentially to create energy, and it goes back to just harnessing the power of fire, and then when humanity figured out a way to bring it indoors, that of course was kind of transformative, and then along the way, after all the wood was kind of stripped out of nearby forests, then where do you get the fuel? And well, coal came along, and that seemed like a pretty good way of continuing the progress of burning things in order to get energy. And eventually we end up with sort of this contraption, which is essentially a gas furnace. And sort of no fuss, no muss, you hardly even know that it's going on, except that it just continues to work in the background and provide us with heating and cooling. And each one of these has its moment in history where, as an innovation, it was incredibly significant, and it was appropriate to its time. All of them had an appropriateness. But as time goes on, as the number of people using these systems grows, you eventually get to a point where these things no longer are working within our time, and we need to find new ways to address our issues and problems. And so one of the innovative things that has happened is this world of geothermal. And so just thinking about the word geo and the ground and thermal, it comes basically from this idea of there is heat in the earth. The core of the planet is super hot, and there are all kinds of ways in which that heat comes to the surface through volcanic kind of systems, and in Iceland is a great example of how they've been able to take that hot water and turn it into steam that drives turbines. They can create electricity out of it. They can also heat water. They can pipe it. They can do all kinds of things. Well, in a place like Toronto, we don't have those kinds of resources accessible to us, and so we need a different kind of solution. And ours, what we're talking about is in a sense, it's not really geothermal. It's a geoexchange technology. And the basic concept is that the ground remains at a constant temperature of about, once you get below about 5 feet, it stays about plus 8 to 10 degrees. And so there is heat down there, and you can pull that heat out, and you can move it from here to here. And that ends up being an interesting kind of thing. So in the summertime, what happens is that it's hot outside, and you want this to be cool. Well, like a refrigerator, and this still is a tough one for me to wrap my head around, but a refrigerator works not by creating cool, but by extracting heat. And that's what this does. It actually takes the heat out of the house through a heat exchange technology, and it takes it into a pipe that goes down, and the heat is actually deposited into the ground. And as the heat goes into the ground, the water gets cooler, and it goes back up and back into the house, and then you are able to distribute cool. So in the winter time, though, it's reversed, and so if you've got the frost line here, and you've still got your 8 to 10 degrees of warmth in there, then you simply reverse the movement of this water, so that what you're doing is taking the heat from down in the ground and bringing it into the house. So that's in a nutshell what Geoexchange is all about. And as long as the Earth continues to be contain heat and be a constant temperature that you can move heat into and out of, it ends up being incredibly efficient. And so unlike burning things, where you actually have to transform something, and energy is a byproduct of that, this kind of a system moves heat around. So you don't have to generate new heat. You really do move around existing energy. And it's why it ends up being 3 to 4 times more efficient than the most efficient fossil fuel. And so, but what does it really look like? Because that was an interesting diagram, but kind of simple. And well, if you have a house with a lot of land around it, you need to put piping into the ground where that liquid goes, and it either is putting heat in or it's taking heat out. And it ends up being, it requires quite a long loop. If you don't have much room, then you go down. And so just to give you a sense that if you're going, and anything that's urban essentially is going to be in this category, because there's very few times when you've got this kind of space. But farms have been using geothermal for decades, and they've got lots of space, so they can dig 6 or 7 foot trenches, put in their piping, and they don't have to bring in a drilling rig. So this is a little bit more realistic look about things, except this is not the size of it. You have to imagine these things going really deep. But
How deep?
Here we've got the same piping configuration, and here we've got a heat exchange unit. Now, part of the magic in a Geoexchange system is the heat exchanger, and I, to be honest, still don't understand what it is. But it's kind of like understanding how do you take heat out of a refrigerator. I don't really understand that. But it uses pressure as well to create a, it can take the heat differential, which is, let's say it's, I don't know, 0 degrees outside, and you're trying to pull heat out of the ground at 8 degrees. Well, a heat exchange unit, using pressure and whatever other magic that it does, is able to amplify the heat, and so that it actually can generate and concentrate that heat in a way that you can then blow it through your house, and you're actually getting 75 degrees coming out of the heating ducts and that sort of thing. So just wanted to point out that there is this component to it, which is the heat exchange unit here, and it feeds right into a duct system that goes throughout the house, just like any forced air system that you might have. You can also use a geothermal system with a water-based distribution system through the house, kind of like a radiator. So there are different ways you can configure these things. But just wanted to give you a sense of that. If you wondered what a drilling rig looks like, here is one attached to the back of a truck. They've got about a 30-foot height that you have to, if you're moving trucks and these things around, going up 30 feet means that you have to really think about what is above ground wherever you want to do drilling. And in the Laurier project, we had to deal with that because of overhead wires and all that. And then there are some that are sort of purpose-built devices that are more like this, and they've just got their own little system for maneuvering. They aren't attached to a typical truck. So, an overview of Laurier Avenue. This is Laurier Avenue, tiny street, 22 homes in Cabbagetown. And the reason where I'm talking to you about it is that we got a grant from Live Green Toronto back in 2008. And we had gone to, they have a whole grant system through the city, the Toronto Environment Office, and we had proposed that we would get our street together and we wanted to explore the possibilities, the feasibility of converting these heritage homes built in 1888 to geothermal heating and cooling, and we thought that it was a great prototype for the city to think about powering the existing building stock. So if any of you are looking at energy efficiency, you've encountered this thing that, okay, if you want to build something new from scratch, you can do that very efficiently and achieve high levels of energy efficiency. But if you want to retrofit an existing building, it's a whole other ballgame. Lots of obstacles to deal with there. And of course, the city's housing stock and building stock basically exists. So if Toronto is going to, and there is about as much, I think about 30%, 35%, something like that, of Toronto's greenhouse gas emissions come from buildings and how buildings operate, mostly because they're associated with burning fossil fuels. And so in order to address the city's carbon issues, ultimately you have to figure out a way to deal with the problem of the existing building stock. And so retrofitting is the big challenge. Building new is not so much of a challenge. There's lots of good stuff out there. So we pushed the city and said, we really want to see if we can do something that will become a bit of an inspiration for other neighborhoods and things like that. This is at a time, though, when the Eco Energy Grant Program was being operated jointly by the province and the feds. It no longer is. It stopped a couple of years ago. But its whole orientation was house by house. And so we had to rally all of the neighbors together to try and figure out how we might do this on a house by house basis, because it was based on that kind of funding situation. But anyway, we got our $25,000 grant. We hired an engineering firm to do our the engineering part of all of this, and it was an amazing thing. But David Miller was a big fan and supporter. Our councillor Pam McConnell was tremendous ally in all of this, and so that's me with Sam and David Miller. So what was Laurier Avenue? 22 row houses, 1888, about 1,500 square foot each. They're heritage homes, and they're designated heritage homes. They're all heated with natural gas and oil. And as you can see, there's very little private property there. And no viable access to the rear of the houses. It's pretty compact little street. And so what our purpose was to assess the opportunities and obstacles of energy efficient retrofits of heritage homes. And one of my interests is Toronto is a city of neighborhoods, and we want to be able to preserve those structures. It's not an option that we just kind of bulldoze the city and build new because it's efficient, right? We have to find a way to keep the character of the city, the heritage of the city intact. So we wanted to compare energy efficient technologies. We wanted to identify financing possibilities, to assess the potential of permeable road resurfacing. So we knew that we had to dig up the street, because the only place that you could put boreholes for these systems would be in the street. You can't get a drilling rig close enough to the house to put them on private property. So we thought, if we're going to rip up the street, then let's do some experimentation on permeable road resurfacing, so that we can retain the surface water runoff locally, rather than putting it into the sewers. And develop a plan for implementation. And we wanted to bring together our neighbors, and our partner in this was the Donville Cabbagetown Residents Association. And we hired a company called Resco to do this, and you can see that some of the obstacles that we were dealing with was there's a storm sewer system that runs down the street itself. We've got sanitary systems that were running along the backs of the houses, and we had water and gas lines that were also under the road. And we had to figure out all this stuff. This is a good prototype because this is how the city is built. And out above the ground, we had to deal with these kinds of wires and virtually no yards. And there's trees in there too, so lots of obstacles. So I just wanted to remind you of what the street looks like as I go into this. So this is a section detail of the front of a house. That's a footing. And this is the front wall of a house. And here you can see the basic concept of having a geothermal system, piping going out and then down 400 feet. One borehole 400 feet down would be what each house would require in order to heat and cool it using a 3-ton heat exchange unit. And you can see that in the front, there's just not a lot of space, especially, and you'll see it in a minute, with the right-of-ways. Again, just to remind you of where we're talking about bringing in these drilling rigs. And this is a drawing that I made. Again, this is a footing of a house, and you can see that this is the so the property line comes out to here. This is the ground along here. So this is what would be considered private property. This is the city right-of-way. This is the sidewalk, and then we drop down, and this is the street here. And so what we worked through with the engineers was digging a hole 1.5 meters square and 1.65 meters deep, down like this, and then we would get horizontal, and we would drill the drilling, vertical drilling down 400 feet, but we'd then get a different drilling company to come in to do horizontal drilling that would come over and into the foundation of the house, and we would go through the various things. There's a water line here, a sewer down here, and a gas thing there. But the locating technologies for all of this are really precise, and you can get the technicians, they can guide this kind of thing. So it was an amazing thing, and one day we had the City Toronto Environment Office, the Transportation Department, the Heritage Department, the Forestry Department, our neighbors, and the DVCRA all on street, and we were starting to look at where we were going to put these holes in the ground, in the road, that we could do this. And we had a fairly long-standing relationship with different parts of the city, and we had worked through a lot of issues that we were moving forward. And the Transportation Department, they're the ones who were always there, but they never gave us anything in writing. And I should have been wise to that, but it ended up being a problem. Late in the game, they changed the rules. They told us that they would be able to sign off on behalf of Enbridge, so that we didn't have to go and get an approval from the gas company. And they also did not say anything about any of these issues. But at the 11th hour, they told us that we would not be allowed to come within a meter of any of the city property that was underneath here. And so that became really the water and the sewer were the two big ones. And so what's the implication of that? Well, I can show you what the implication is. This is again a section, same house, but now in order to do this, I can't remember what the actual figure was, but in order to miss this, the storm sewer and the water by a meter, we couldn't go above the water. That would take us too close to the surface. We had to go a meter below the sewer, and that meant that we would have to drop this hole down to, I'm not sure I can read it. It was more than 12 feet. And in order to get down 12 feet and then do horizontal drilling, you have to make the hole gigantic in order for the angles and everything, to get the equipment in to make these things work. So I did these drawings sort of at the last minute, and it was one of the last straws for me. And before we abandoned it, but it was a pretty interesting exercise to go through. I'll just continue here, and we'll come back to what happened with Green Laurier. But the opportunities for geothermal systems. What we learned through the study was that bar none, there is nothing that is more efficient than geothermal for heating and cooling. And 1 unit of energy input will give you 3 to 4 thermal units of output. And so now to compare that, if you've got the most efficient gas burning system, essentially you will get very close to, but not quite to 100% efficiency, like one unit in will give you 1 unit out. Oil is considerably less than that. But here you get this high efficiency, and it is really the telling thing that then you've got no greenhouse gases coming out of any of this except what you need to generate the electricity. And so, but the systems are quite efficient. So anyway, this is the final ultimate sort of result of the efficiency analysis. The technology is reliable, well tested. It's been around for decades. It provides long-term energy and service strategies. It'll help preserve neighborhood heritage architecture. Low greenhouse gas emissions limited only by the electricity supply. And if there was the rollout of a geothermal utility retrofitting the entire city, all the buildings with geothermal systems, it would have a much bigger impact than N-Wave. Now, are you familiar with N-Wave?
No.
It's the deep water cooling system that and I think you're going to talk about it, right? But,
A little bit,
yeah. But N-Wave, the city just sold off its share in N-Wave, but it is using the cold water from deep in the lake, pulling it out and sending it through the office towers downtown to cool office towers without having to use the conventional air conditioning systems. And hugely efficient, but it is a form of this geothermal concept. And so this kind of utility would have a massive impact on the city's greenhouse gas emissions. And it also addresses a critical aspect of the city's Power to Live Green plan, which the city has an environment plan called Live Green Toronto, and then it also has an energy plan called the Power to Live Green. And it's a very interesting document. I don't know what its status is since the last 4 years went on, but well worth having a look at. So obstacles, high capital costs, and a lot of that comes from you have to bring in a drilling rig and you have to make holes 400 feet into bedrock. Lack of awareness of geothermal technologies. People they don't know what options they have. And they're definitely in a high density city, there's a lack of accessible private property. But it's interesting that Jack Layton and Olivia Chow in their house put in a personal geothermal system like the one that we've been talking about in their house. And so it has happened on individual level, but it's more costly. No streamlined approval system for geothermal. One of the things we realized that we were being encouraged by Live Green Toronto, the city, to do these kinds of things. And then we ran into amazing obstacles from other departments in the city. And so when we got through the feasibility study, we eventually said back to Toronto Environment Office that if you want us to push further, you're going to have to help us to actually come to make this real. And they did. They gave us a staff member to help us navigate through the City Hall. And it was amazing. We got a lot accomplished. We ended up eventually giving up, but not without a huge amount of success along the way. But one of the things we realized, there's no real system for getting approvals for a geothermal system. High fees for implementation. Because we were going to use the road, they saw us as the same kind of interest as an Enbridge, and they charge Enbridge for the, I believe, because they seem to suggest that anyone who was going to access land under the road they'd have to pay fees to gain access to that land, and then an annual fee beyond that. Crazy stuff. Well, we ended up having those fees waived for us if we had managed to actually get it happen. to happen, but they still are there as far as I know. Need interior retrofits to maximize geothermal benefits. And that is you do have to do everything that you probably already engaged in, especially with insulation, to make sure that the house is a well-sealed, efficient envelope in order to make these systems work well. And we did realize that the one house at a time doesn't make much sense. We realized that what we went through, and if we had been successful at getting, I think in the final analysis there were 6 of us on the street willing to go forward until we eventually ran into obstacles we couldn't deal with. But even if we had 6 out of 22, working one house at a time is not the way to go. The way to go is through a district system. It's more efficient, and it addresses the scale of the problem that Toronto has with a huge building stock, all of which is inefficient. So how did it end? Well, we submitted our report. The Toronto Environment Office helped us navigate City Hall. We had huge support from Pam McConnell, David Miller, Glenn Murray, our MPP. But we watched costs escalate. Some more and more of our neighbors withdrew as the costs got higher. There were many parts of this that we didn't know when we started, all of which have a cost. City Council, the Community Council ultimately approved Green Laurier conditionally. And the conditions were that we met the requirements of the Transportation Department. That's really what killed us. But the other thing that was going on was the end of the Eco-Energy grant program was coming up, and we didn't have we weren't confident that if we had gone forward that we would have gotten all the work done, had it inspected, in order to get the grants. And we really couldn't afford this if we didn't have those grants, the $10,000 a house grant. The Transportation Department threw up obstacles that we couldn't overcome, and I don't know why they weren't way more upfront about that at the beginning, because we were definitely talking to them. So we gave up. But one of the big lessons there was learning about district systems, and it's the way to go. So, district systems. We've got some amazing local examples of district systems. And this is the University of Ontario Institute of Technology out in Oshawa. And it actually houses what I think is still the largest geothermal array in Canada. And I think the second largest in North America. And I can probably tell you, well, I'll get to the figures about it, but you can see that there is a cluster of buildings that, and they're all being fed by this amazing number of boreholes. And this is not the actual number of boreholes that's there. There were far more than that. But this is the site when it was in the midst of going through its development. So it was. There was a $5 million capital cost to do this, to make it entirely powered by geothermal, both the cooling and the heating side. But it only had a 7-year payback period for the whole system. So 375 thermal wells had to be drilled 200 meters deep. So an amazing amount of drilling. And down below here are 80 kilometers worth of piping if you laid them end to end. And so this is what the building configurations are like, and this is the bore field. And I learned about, I was teaching a course at George Brown called Sustainability of the City and You about 10 years ago. And I had a colleague who's a hydrogeologist. And I didn't know anything about geothermal then, and she came in and she showed me all this, and they had finished doing the bore field for all of this, and And this is where I got the idea for Green Laurier, was from Joanne. And this was just such a stunning example of the power of this new technology. But also closer to home, at 92 Carlton Street, Toronto Community Housing has been working with district systems, and this is a district geothermal system, and it's an old historic building where they kept, I think it's basically just this facade. It was, there's nothing there but that facade in terms of heritage. And this entire building, which is community housing, is built on top of a bore field that is underneath the building. That's how confident they are in the technology that they put in the bore field and then build the building on top of it. And so this is an example of the city actually taking up this kind of technology and applying it within their own frameworks. And one of the impacts of the work that we did with Green Laurier is we attracted the interest of some architects who are really into energy, and they came to me and said, "Well, what would you think if we tried to sort of spin the Green Laurier thing into a larger district thing?" And their idea was, this is Finn Park. It's over in Riverdale. And it's an amazing site because you've got all of these houses along here and down here and up this way. These ones over here are Toronto Community Housing. This is Eastern Commerce, I think it is, high school. So TDSB has been doing work on geothermal, interested in these kinds of things. If you can get this kind of multi-use prototype project going on somewhere, I think they are really exciting prospects for understanding what it would actually take to transform the existing building stock using these kinds of technologies. And you put the bore field underneath the park. It's not going to, I mean, it's a mess while it's being drilled, but ultimately, if we think about this, it doesn't require drilling under the roads, and this is a lane that runs along here. So it's not actually a road, and I think that probably makes it easier to deal with the transportation department than we had to. And so all of these houses are backing onto the park. So it was really kind of an ideal thing, but it's the kind of project that I think is really required in the city to move the ball down the field, as it were. So next steps. I think that prototypes and tests in district geothermal systems are required. To develop some provisional visions of a retrofitted city of Toronto with energy efficiency in mind. So at this point, I don't think there is a real vision of what the city as an energy efficient place is. Not that people have a sense of connection to. If anybody's got these visions, they're kind of isolated, I think, and people don't feel connected to them. So Project Neutral, I'm sure, has an image of what this looks like, but it's not well integrated into the fabric of the larger community. District systems will require a utility to plan and manage a large-scale rollout. And so I've talked to the people at the city about this, and I've even talked to some folks at Toronto Hydro and at Enbridge about it. But that's the kind of thing that's required. Somebody, some organization that can actually take on a monstrous task of planning around the retrofitting of the city's buildings using these kinds of models. And we need greater public interest and a sense of agency related to renewable energy. And we are seeing more and more things like Green 13 and Project Neutral and Green Laurier, and those are exciting. But you can only bang your head against some of these walls for so long before you get pretty tired. So anyway, that's my little story.
Or we have time for a few questions.
I didn't understand, like, you showed the diagram at the beginning and you were like, as long as you go down like 5 to 10 feet, it's like 8 to 10 degrees, and then you're like, when we did it, we had to go to, if we were going to do it, we had to go down 400 feet, and like why can't you just go down like what you explained at first was that it was very close to the surface, this balanced temperature, and then you were like, we have to go even further. So I totally missed what was going on there.
Okay, it's a good question, and so if you're trying to take heat from a house and put it into the ground, you need a lot of ground that is going to take that heat, and so you need this linear distance to be able to deposit the heat, because you're distributing it over a large area, so you're not taking that heat and concentrating it into an area that becomes hot. You're just elevating the temperature a bit, and so you need that length to be able to take enough heat in order for the heat exchange unit to be able to do its thing in amplifying that differential. I don't know whether that helps. But
Depend also from the terrain, how is the ground, the geological aspect. Because I have a colleague that they've done in Europe, one 50 meter and the other 81. That is much less.
in Toronto, at least over in our area, we found that there's about 75 feet of what they call overburden, which is dirt and rubble and things like that.
Cannot
which is,
disperse the heat.
and then it will absorb heat and give it back, but it's just another part of what you have to deal with. You're absolutely right. You need to know what is underneath there. What are the obstacles that you're into? The drills don't have any problem going through the rock. They do have problems when they run into odd things that are down in the dirt.
What? Sorry, odd things?
Yeah, like big, like if you run into sort of odd outcroppings of rock. So if it's an even rock, they can drill through them. But it's called overburden, and I'm not a geologist, so I don't really know what it is. But there's a lot of sand, right, in downtown Toronto, because it's the lake used to go all the way up to there.
I know that area where that park is. I lived there for years.
At Finn Park?
Yes, at Eastern High School of Commerce. There's a Lost Creek there, and it was all open in 1912.
Oh, yeah.
Over 100 years ago.
Right.
And landfill has since taken place. So the remains of the creek can be traced, but it's all gone, of course.
Uh-huh.
And so you have, as you say, that overburden. So it's kind of interesting how it's changed in 100 years.
Mm-hmm. I think the point is that from a technical point of view, the drilling is a critical step. You need to be able to drill, and you need to be able to put your piping down into the ground. And so usually the drills don't have any trouble, but they can run into some trouble. And they just have, these are problems that they know how to solve, but I just thought I'd point it out. It's not always straightforward, yeah?
The boreholes, it looked like from your diagram that they're fairly close together. I would think from what you say that you would have to space them out a bit in order to keep from overheating.
That's right. You're absolutely right, because you need these calculations of how much heat are you actually going to take, mm-hmm. and how much are you going to put into the ground, and how much can it absorb. And so you do need to figure out all of that.
So who are these people that are doing all of this? I mean, obviously there's not too much geothermal going on, so they must be doing other things besides doing geothermal.
Well, there's
people with the drills and the people with the calculations and so on.
There are companies that do geothermal systems.
Just geothermal?
I think so. But I'm not entirely sure. But we were talking to drillers. We talked to a number of drillers, and so they're out there, and they seem to know what they're doing. I mean, what do we know, right? And so it's a great question. The other related question to that is, the larger projects run into this, is you have to find a balance. So and I think it has to do, the implications are for how you space out the borehole. So if you take a lot of heat from the buildings in winter, or in the summer, and put it into the ground, you need to basically, in the summer, take, you need to balance these things. Whatever goes in one year in the winter needs to come out in the summer, and vice versa. And because over time, over several years, you can actually, if you haven't planned it properly, you can end up heating the soil to a point where it's no longer good for taking cooling out. Or it's not as good as it was when you started. So these are all part of the calculations, but it is the fine point of.
One last question.
I was kind of, my ears really perked up when you kind of were talking about the transportation obstacles. And I feel confused that you're in partnership with the mayor of Toronto working on a project, and then you have another section of Toronto who's like forbidding you from doing it. Sounded like there was some politics involved, and that just seems really messed up. Like, I feel like part of the conversation needs to be like, if we're going to do this, we need to have everyone on board, and if someone like the mayor is like approving it, then they should also be able to, like, you know, be in contact and maneuver and be like, no, like, it just kind of seems, I don't know, weak is the word that comes to mind. Like, I'm just like, really? Like,
Well,
what happened?
It's not as arbitrary as that, because the transportation department is governed by all kinds of regulations and laws about how the roads get used, and all kinds of things. And then there's professional things. So there's regulatory things, there's engineering things, building things, there's codes and all of that. And so something like geothermal is outside of the norm.
But so will all sustainable solutions, so it's like, that has to be in the conversation. It's like, you know, a lot of laws, they just make them, but you never see people really take them away, and that's an issue.
I think it is an issue.
But therefore, there is not yet an office where I say I want to do a geothermal system in my house. Up to date does not exist in Toronto, an office where I present my project.
I think now, one of the things that happened as a result of us at Green Laurier is that they were working on a single sheet, because in order to do a geothermal system, we had to go to heritage and forestry and roads and all kinds of departments. And so they now have put together some kind of form that if you're going to do this, there's one sheet of paper. Now, I don't know what that really means. Do they just Xerox it and send it to?
We're in the geothermal business, and our biggest challenge is Ministry of Environment. They actually froze the license of geothermal company for 1 year. So now that we're back in business, basically for anything geothermal, we have to do preliminary evaluation. The reporting is horrendous. And well, I mean, we still do the job, we still do projects, we're working on bigger projects than even a bigger district energy. We're working on cogen models with solar, and being where solar could heat up the ground and so forth. And but you know, even one of our directors, who's a pioneer in geothermal, Gino Di Resi, probably you.
Gino, I met Gino.
Yeah. So basically, asked him to come and stay and say hi. He met the Ministry of Environment. He loves the technology, and we just asked him, why don't you guys promote us? Why don't you help us to be able to spread the information to public and so forth? And of course, the oil and gas companies, they're going to lose money. So obviously, there is no conversation in any of them, because hydro wants the profit, and that's another big challenge. Because if you look at, there's like finance for everyone except geo. Like people in solar, they have all kind of money available to them. So that's our challenge, right? And but it is what it is. And this, when we're not busy, we do other things. We do retrofits, we do radiant flooring. We also with drilling companies, they do well drilling, and so we keep ourselves very busy.
Yeah.
So it's an interesting field, and
Well, I'm sure there'll be some questions for you, because you know it from the inside.
One thing that was sort of not in your presentation, except for the 5 million for the university, was money. So I'm just curious, like, what would have the cost been if you did the 22 buildings? And also, like, if you're building a new building, like, what is the increase on your capital cost to dig down?
Well, it may be different now than it was then, but I think that we were looking at, for our houses on a per house basis, we were looking at, I think it ended up at around $35,000, and then
Per
we would
house.
get per house, and then we would get 10,000 back from the government, and
Which level of government?
well, partly feds and partly province, but now both of those are gone.
This is pre-2006?
It ended in 2012?
Yeah.
Well, it ended in 2011, I think, and then it started up again for a year, and then it was kind of a sad little whimpering.
Yeah. It started up, but not really.
And then for like a new building, like let's say you're building a building and it would cost 10 million, but you're like, let's add the geothermal. How much more than the 10 million for like a big tower or whatever would it be?
Well, I don't know, but you saw the University of Ontario.
Yeah.
That was,
Yeah, we have two more presentations, so I'm going to call the questions and I'm going to welcome Johanna to come on. Thank you very much, Douglas. That was really, it was a great presentation.